right, so now we're talking about inferences on two samples. And what this is doing is extending what we've already seen in chapter 10, and we're extending it to two samples now instead of just looking at one. So it's going to be very similar. The formulas are going to be different. They're going to be similar, but they're just going to be longer since we have this added sample. And so let's just talk about first independent versus dependent sampling methods here. So a sampling method is independent when the individuals selected for one sample do not dictate which individuals are to be in the second sample. A sampling method is dependent when the individuals selected to be in one sample are used to determine the individuals in the second sample. Dependent samples are often referred to as matched pairs. It's possible for an individual to be matched against him or herself. So we're just going to focus on doing an example here of independent versus dependent samples. So example 1, determine if the following is independent or dependent. There are 1,200 students enrolled in a traditional lecture math-based course. 300 are enrolled online in an online math-based course. Once the course ended, the researchers determined whether the student passed the course with an A, B, or C. The goal of the study was to determine whether the proportion of students who passed the lab-based format exceeded that of the lecture format. So this is a great example of inferences on two samples. So here, this would be independent because our two samples, which are the 1,200 students in the lecture-based course, which means in class, traditional, and there's 300 online. So those are our two samples, and they're not connected in any way. Picking one student in this 1,200 sample does not dictate which person we pick over here in this 300 sample. So we can say independent. One course does not affect the other. All right. Number two, part B. Do women tend to select a spouse with a higher IQ than their own? To answer this question, researchers randomly selected 20 women and their husbands. They measured the IQ of each husband-wife team to determine if there's a significant difference in IQ. So here, hopefully you can see this is dependent. It's dependent because we're selecting 20 women and their husbands. So by selecting a woman in the first sample, it automatically picks the husband that's attached to them. So this is what you would call a dependent sample because the husband depends on if their wife is chosen. So let's try to write that. Dependent because once the wife is selected, so is the husband. That is, the husband depends, that's the key word, depends means dependent, depends on the wife being selected. That is, going back to this other term we set up here, matched pairs. Sometimes they're referred to as matched pairs. That is, the husband-wife team is a matched pair. All right. Now let's get into, so that's the terminology there. Now let's get into how we determine the mean, the standard deviation, and then we'll look at the how to find the z-score of something like this, and then the test statistic, and then we'll form our hypothesis. We'll do our null and our alternative. So everything from here on out is going to be very similar to Chapter 10, just with different formulas. So let's start. Suppose a simple random sample of size. Now there's going to be remember there's two samples, so there's also going to be two different sample sizes. So here, a simple random sample of size x1 is taken from a population where n1 of the individuals have a specified characteristic. You could view this as in part A up here as the 1,200 students enrolled in a traditional course. That's what this x1 and n1 would represent. And a simple random sample of size x2 is independently taken from a different population where n2 of the individuals have a specified characteristic. That would be the 300 enrolled in the online base math course. So that's how we will start labeling these things. The sampling distribution of, and here we have P1 hat minus P2 hat. That's now the sampling distribution. Instead of just having P hat, where we're looking at one sample at a time, now we're looking at two samples. And so this is how we label it. And to determine P1 hat and P2 hat, it's exactly the same as we did just regular P hat. P1 hat is equal to x1 over n1, and P2 hat is equal to x2 over n2. So that's how we set up the proportion. So far it's very similar. It is approximately normal with mean, so the mean here we still label as mu. P1 hat minus P2 hat is equal to P1 minus P2. All right, so remember, this is just telling you, this mu is telling you that we're looking at the mean, and the subscript is telling you what type of sample or population or proportion that we're dealing with. We've seen X bar, we've seen P hat, now we see this. All right, so that's the mean, and then the standard deviation is kind of big. So let's see here. The standard deviation of P1 hat minus P2 hat is equal to, and you may want to not pause, but you may want to watch me and then pause the video to write it down. So there is P1 times 1 minus P1 all over N1. And so far that's very similar to what the standard deviation looked like for just P hat. But now we have to add on the P2. P2 times 1 minus P2 all over N2. And then all of that is square rooted. So if you remember back when we were just doing sigma of P hat, it was just, take out this second term, it was just this and the square root. Now we just added on this second term. So very, very similar. And that's provided that it satisfies these two equations, and I did not leave myself enough room here. It's N1 times P1 times 1 minus P1 hat is greater than or equal to 10. So what we've seen before, except now we have to include the two versions here. So we have to check both of these now. Oh, and there's supposed to be hats there. All right, so just a quick check of those and then we're off and running. The standardized version the standardized version of P1 hat minus P2 hat is then written as the standardized version, meaning Z. Standardized version is the same thing as Z because that puts everything in terms of standard deviations relative to the mean. So this is quite big also, so this is another thing you probably want to watch and then pause. So remember the standard deviation is always on the bottom, so this is the standard deviation, so that big thing goes down here. So I'll go ahead and write that in first. And then the square root of all that. And then on the top, it's the same thing as before, except now we have two terms. It was p hat minus p. Now it's p1 hat minus p2 hat. Whereas before this was just p hat. And minus then p1 minus p2. Whereas before this was just p. So it's just an extension on what we've done already. All right, so pause the video if you need to do that. I'm going to go ahead and go on. So that Z formula I just wrote, which is, let's get down here, which has an approximate standard normal distribution. We will use this formula again later in the section. For now, we look at the test statistic, Z naught, which we can derive from the formula above, the Z formula that we looked at, by using some algebra, but we're not going to look at how to derive that. I just wanted you to know that's where it comes from. So we had a test statistic in chapter 10 also, and we'll have it here. And it will be a little similar, but here it is. So I'm going to start over here. Z naught is equal to, and again, you may want to watch first and then write. The top is P1 hat minus P2 hat. Then the bottom, this is where you're going to want to watch. It's P hat 1 minus P hat, the square root of that, and then that's multiplied by the square root of 1 over N1 plus 1 over N2. And here we need to define what P hat is, so that's a comma there. P hat, where P hat is equal to x1 plus x2 all over n1 plus n2. So we're adding up the two samples divided by the two characteristics that we wanted, and divided by the total sample sizes there. All right. Let's look at an example here. All right. In a clinical trial of Nasonex, 3,774 adults and adolescent allergy patients 12 years or older, were randomly divided into two groups. The patients in group 1, the experimental group, received 200 milligrams of Nasonex, while the patients in group 2, the control group, received a placebo. Placebo meaning they just received a pill that does nothing, just basically sugar. Or just basically water, however they were taking the Nasonex. Of the 2103 patients in the experimental group, 547 reported headaches as a side effect. Of the 1671 patients in the control group, 368 reported headaches as a side effect. Is there a significant evidence to conclude the proportion of Nasonex users experience headaches as a side effect is greater than the proportion of the control group at alpha equal 0.05 level of significance? All right, so treat this problem exactly like we did in chapter 10, except now we just have an extra sample to worry about. And we'll use the same formula. We'll use this the statistic up here, and we'll follow the same steps as in chapter 10. Step 1, I'm not going to write out all the details, all the words, because I wrote those down in the previous chapter. But step 1 is to check N1 in P1 hat times 1 minus P hat, P greater than or equal to 10. And we want to check N2 times P2 hat times 1 minus P2 hat is greater than or equal to 10. All right? So to check those, I'm not going to go into the actual checking of them. They work out here. But you need to know when you check it, you need to know what P1 hat and P2 hat are. So remember, P1 hat is equal to X1 over N1. All right, and we can call these the experimental group. Okay, so out of the experimental group, let's see, we had 2103 patients in the experimental group and 547 reported headaches. So it's 547 all over 2103, which is equal to 0.26. And then P2 hat, this is the placebo group. That's X2 over N2. So we come find our second sample here. And we had 1671 patients and 368 said they had headaches. And that is 0.22. So that's how you would find P1 hat and P2 hat and plug it in here. And you're going to have to know these in a later step anyway, so it's good to just get them out of the way. Step 2, we need to determine our null and our alternative hypothesis. So remember, let's label. P1 is the Nasonex group, and P2 was the placebo. So that's just to kind of help us remind us when we write our null and alternative here. So H naught is if it's equal. Remember, H naught is unchanged. Nothing's changing. H1 is what we're testing. H1, the alternative hypothesis, and let's see. Is there significant evidence to conclude the proportion of Nasonex users that experience headaches as a side effect is greater than the proportion in the control group? Greater than is the key there. That means it's one-tailed. In this case, it's right-tailed. So we want to know P1 greater than P2. Okay, so that sets up our null and our alternative. Step 3 is to determine our level of significance and our critical values. So we know alpha is equal to 0.05, which implies we're at a 95%. All right, so we want to find, since it's one-tailed, let's write this in a different color. Since one-tailed, kind of abbreviate it, since it's one-tailed, we use what? Remember, if it's one-tailed, we use Z alpha, and if it's two-tailed, we use Z alpha over 2. So since we know alpha is 0.05, all right, that gives us a critical value of 1.645. All right, so now what we want to do is we want to draw a graph. A graph always helps. It's supposed to be step 3. A graph is always useful. So here. And let's plot our critical value of 1.645. This is 1.645. And here is our critical region. Now let's refresh what it means. So next step is to work our test statistic. And when we do that, that gives us a Z value. And if that Z value is in our critical region, that means we reject the null, H naught. And if it's not, that means we do not reject the null. So now we need to find our test statistic. step 4. So let's write the formula first. It's Z naught is equal to this big ugly thing okay, and now we just plug in everything that we know. So this is equal to P1 hat and P2 hat we found up here in step 1. Okay, you can find those at any time. So we already got those out of the way. So that was 0.26 minus 0.24. And then on the bottom, we have P hat minus 1 times 1 minus P hat. So we have to determine what P hat is here. All right, and I showed you up here, we're just going to slide up, where P hat is equal to this, x1 plus x2 over n1 plus n2. So we have all that info, so I can come over here on the side and say P hat is equal to x1 plus x2 all over n1 plus n2. And then plugging in those values, x1 was 547 plus x2, which was 368. I'm just copying the values here. I already found what x1 was in n1 and x2 and n2. So I'm just plugging those in down here. And do the math there, and you get 0.242. So that's what we plug in down here now. So we have the square root of 0.242 times 1 minus 242. And then that's multiplied by the square root of 1 over n1, which is 2103, plus 1 over n2, which is 1671. So if you were to plug this in the calculator, just take it step at a time, because this can get pretty hairy. But when you do this, you get 2.85. All right, so what that's saying is our test statistic is 2.85. So we come up here and we say, here is Z naught equal to 2.85. And does that lie within our critical region? Yes, it does. So we can say since 2.85 is in the critical region, we reject the null. Okay, so very similar to what we've already done. We just added an extra sample on here. All right, the last thing I want to talk about is constructing and interpreting confidence intervals for 2 samples like we're doing here, or 2 proportions. So constructing and interpreting confidence intervals. So again, you'll find this is very similar to what you've already done. And so I'm just going to show you the formulas here, and then I'm not going to do it for you, but I want you to plug in the values and find the confidence intervals yourself. So the lower bound it's similar to the lower bounds we've already learned, just adding on that extra P2 hat. So it starts out as, I'm going to do it down here, P1 hat minus P2 hat minus then Z alpha over 2, and that's multiplied by this big square root, which is the standard deviation. P1 hat, 1 minus P1 hat, all over N1 plus P2 hat times 1 minus P2 hat, all over N2. So this value you already know. this value minus z alpha over 2, we found that in the previous, if you wanted to do it for the problem before, we found that value to be 1.645, and then this we've already calculated in the previous example also. And so then the upper bound is the exact same formula, except now we have a plus. Plus z alpha over 2, and then times the standard deviation. All right, so there are the confidence intervals. What I want you to do now is, when the video is over, is go back and work the previous example that we just did regarding Nasonex and find these two. That's it for now.